We are glad to present our paper titled CAD-Assistant, Tool-Augmented VLLMs as Generic CAD Task Solvers. Recently, there has been a significant research interest in CAD automation. Still, most research efforts focus on fixed CAD workflows. Examples include 3D reverse engineering, edge parameterization, multi-view CAD reconstruction, and hand-drawn sketch parameterization. In this work, we shift the focus to foundational vision language models and explore their potential to act as general-purpose CAD agents that enable AI-assisted design. Still, the use of vision language models within CAD workflows remains limited due to their weaknesses in geometric reasoning. These models might struggle to semantically interpret CAD sequences, recognize the spatial arrangements of CAD features, or correctly position geometric primitives. Moreover, high-level CAD operations such as fillets or chamfers can produce complex changes in geometry that language models are unable to predict. In this work, we introduce CAD-Assistant, a tool-augmented VLLM framework that integrates CAD-specific tools to address the limitations of vision language models for CAD design. As a generic CAD task solver, CAD-Assistant can address multimodal input queries in a zero-shot manner. CAD-Assistant integrates a wide range of CAD tools. CAD code is executed directly within FreeCAD accessed via its Python API. Geometric reasoning is enhanced by dedicated CAD recognizers. CAD tools include also a hand-drawn image parameterizer, a handcrafted routine for geometric constraints analysis, and a 2D cross-section generator for processing of 3D scans. CAD-Assistant is a training-free framework that can address common CAD tasks on a zero-shot manner. We evaluate our method on hand-drawn image parameterization, CAD question answering, and CAD autoconstraining. Beyond these benchmarks, we also demonstrate real-world use cases such as generating 3D solids from hand-drawn sketches, processing drawn CAD commands, and performing 3D reverse engineering through cross-section parameterization. Let's provide an overview of the CAD-Assistant framework. A multimodal user request is provided as context to a VLLM planner. For each time step, the planner generates a plan and action expressed as Python code. For example, at time step t=1, the planner is invoking the sketch parameterization tool to process the hand-drawn sketch image. The code action is executed in a Python interpreter that directly integrates the FreeCAD software and is also equipped with a toolset of CAD-specific tools. Execution feedback is fed back to the planner, enabling generation for the next time step. The process iterates until the planner concludes that the request has been addressed. At that point, a special terminate plan is generated, indicating the completion of CAD-Assistant's response. Let's look at the trajectory generated by CAD-Assistant for an auto-constraining request. To begin, the planner uses the CAD sketch recognizer tool to analyze the current state of the sketch. The tool call is executed on the FreeCAD-equipped Python environment and returns both a summary of geometries in JSON format and a visual rendering of the CAD sketch. After recognizing the sketch geometry, the planner generates a set of coincident constraints to connect the sketch vertices. It also uses the constraint checking utility to ensure that the applied constraints do not significantly distort the geometry. The corresponding Python code is executed, and the changes are applied directly to the FreeCAD sketch. The process continues until the planner outputs a terminate plan, marking the end of generation. At this stage, the CAD sketch is fully constrained. In this work, we identify that tool augmentation can effectively mitigate the limitations of vision language models on geometric reasoning. CAD representations that are derived using external tools can improve the planner's understanding of CAD programs. We study different parametrization strategies, as geometries can be represented by different sets of parameters. We also ablate different serialization formats used to convert the parametric geometry into text and investigate visual representations for geometric reasoning by providing the vision language model with 2D renderings of the CAD sketch or 3D solid. To examine the impact of these strategies on CAD program understanding, we experiment on SGP Bench. A planner is provided with different CAD representation and tasked with answering a multiple-choice question about the design. We observe that schema-embedded representation like JSON performs better than tabular formats. GPT-4o demonstrates high sensitivity to geometry parametrization, and rendering-based question answering surpasses the performance reported for text-based recognition. These findings motivate the design of optimal recognition tools that are provided on the CAD-Assistant toolset. To address the lack of benchmarks for tool use, we adopt an evaluation setting for generic CAD agents based on existing CAD tasks. CAD-Assistant outperforms both vision language baselines and supervised task-specific methods trained on large-scale datasets, despite being prompted in a zero-shot manner. Thank you for listening. You can learn more about CAD-Assistant by visiting our project page or GitHub repository.